Okay, I guess we can start. Welcome everyone. And today we have a talk by Barak Gabai about exact quantization. Please, you can start.
Okay, thank you. So what I'll discuss today is, I would say, the more rigorous version of exact quantization in quantum mechanics, which is a bit of a pathological sentence. I'm saying quantization in quantum mechanics, but I just mean to say that it's not about QFT. I'm discussing specifically a simpler 0+1 dimensional model. Specifically, I will talk about these two Schrodinger equation. So maybe one can even think about this as just a mathematical method to solve these equations, but it's very physically motivated and specifically suitable for applications that physicists care about. So everything I will say will be based on our paper from earlier this year and on this paper by Marino, Ito, and Chu from a couple of years ago. I think most of what I would say will already be things that are already in this paper, just because I think that would make the presentation more approachable and more useful. I think if I jump to our contributions, it will not be as useful. So maybe I can say that so classically one-dimensional model like this, I guess this is already the Schrodinger equation, but the corresponding classical model will always be integrable in the sense of action angle variables. So we can always foliate the phase space in terms of invariant tori. But what I will discuss today is to some people surprising integrability in quantum mechanics, which is based on two ingredients. The first is an integral equation, a TBA, that for something we can call the exact periods or the quantum periods that are the generalization of the action variables. And the second ingredient is the exact quantization condition, which is the generalization of the Bohr-Sommerfeld quantization condition. So we can quantize a system in the leading order in W2B approximation by using Bohr-Sommerfeld on the action variables. So here we will use the exact quantization condition, or EQC, on the quantum periods, which are the solutions to the integral equations, to the TBA. So there are many more references. The old work that is kind of started building this up, maybe from a less rigorous point of view, was done by Voros, De La Barre, Pham, and there's more recent work by Marino, except for this paper that I put here, and also importantly the literature on what's called the ODE, ordinary differential equation integrable model duality, which is also mostly from the 90s. Okay. So, sorry. So if I start with this type of equation, the classical periods are let's say if I'm talking about the particle, this is the type of potential I have. Let's say I analyze it without loss of generality in energy zero energy. I absorb the energy into the potential here into into UR. And the classical periods now are, I can look at the turning points of where the potential vanishes, and then I can analyze the square root of V as a function, as a complex function, and it has 4 branch points. And the classical potentials, classical periods are the periods around either any 2 of these turning points. So which is essentially the EDQ, which is the action variable in classical mechanics.
It's a bit unclear what are the powers actually in the equation. I mean, what are the powers of X?
Oh, I'm sorry. So this is the potential with some generic polynomial. The highest power is r+1, and I have some generic coefficients for the rest. I don't have x to the r because I can absorb it into a shift of x.
Okay.
Okay. So we're discussing just some any generic polynomial. This thing, if let's call this gamma 3, gamma 2, and gamma 1 for this period. This thing is called the classical periods, and that's the thing we'll generalize quantum mechanically. So the classical object we'll call M. We define M as the for real parameters is the absolute value of this, and the quantum mechanical project will gamma A M A. Quantum mechanical object we will call epsilon, but you'll see it later. I'm just telling you here so that when it comes up,
sorry. Again, a bit unclear. If it's a generic polynomial, why are there only 2 potential wells? Why aren't there more?
Oh, I'm sorry. So we are going to discuss a generic polynomial in general, but I just made that because I have to choose one specific power to make the plot. So I just, this is an example.
Okay, sure. Yes.
R equals 3. Yeah, sorry. Thank you for asking. That, okay. So yes, of course, in general, we will have we can have many more. So historically, okay, I'll start from now describing how we get the TBA for the quantum exact generalization of this object. Historically, what people were doing was taking this object and then expanding an empower series in H bar in the WKB expansion, and then trying to resum this object. We will take a different approach where I will define a non-perturbative object, and then a posteriori, I will justify why it has this classical limit, and why this is the correct interpretation of this object. Okay, so this potential that this Schrodinger equation that I wrote here is invariant under something that is called semantic rotation. So if I simultaneously rotate the coordinate and all of the parameters of the potential, I get back the same Schrodinger equation. However, if I do this slowly and I track analytically what happens to one of the solutions to the Schrodinger equation, it doesn't have to get back to itself because we have a 2-dimensional solution space, so there can be a change of basis essentially applied by this semantic rotation. And that would be the main ingredient of the analysis here. So more generally, more specifically, if we take the complex plane of the coordinate x, we can divide it into 6 sectors. We can divide it. I'm again specifying to r equals 3 to make things simpler. So this is for quartic potential. So for quartic potential, we can divide it into 6 sectors. more generally, we can divide it into R plus 3 sectors. And here e to the I pi R plus, this line is e to the minus I pi over 6 R plus. And the idea is that the WPV approximation tells us that we can always find the solution that decays in any of these sectors. So specifically, I will define y naught of x, ua, and h bar as the solution that decays in the first sector here. I will call it S naught. So this is the solution that decays when I go to infinity in this direction. And now I want to ask what happens when I apply semantic rotation and track analytically this solution.
Sorry, can you explain why you have a 0 on the right-hand side of the Schrodinger equation?
Yes, I absorb the energy into U and U.
Okay, okay. Mm-hmm.
Yeah, thank you. Yeah, in general, this approach has this inconvenience where you have to first fix the energy and then solve for allowed values of h bar, for the spectrum of h bar. And then after you do it for a grid of energies, you can invert the relation. But yeah, you will see all of that. Hopefully,
I have just a small technical question. I mean, I remember,
yes.
like, say for the Airy function, you can always write like the solution as an integral of some exponential of a polynomial. So I'm wondering, is it always the case for these potentials where the polynomial is, you know, exactly has the right power, so you have all these sectors?
I believe that's yeah, that would be the approximate solution at large absolute value of x. So that's exactly the form that it will take. I don't think I will write it down because it will take me 2 minutes, and that's a shame. But yes, that's exactly the form that the asymptotic solution takes, and that's why we know that we have these sectors. But once we go to finite x, there are infinitely many corrections to that, and we cannot write a closed form expression.
Okay, yeah.
Thank you. Okay, so now let's ask what happens as we apply a semantic rotation to this y naught. So I define yk with some normalization that I choose for convenience, and y naught after k semantic rotation. And what I'm going to do now is I'm going to write this actually as, instead of a semantic rotation, an analytic continuation in h bar. So I'll explain in a moment why this is the same. So the idea this is based on is that the Schrodinger equation is actually invariant under x to some number to a certain power times x, ua to and it's not 2a plus 1 and h bar to lambda h bar. So because the Schrodinger equation is invariant under this, I can imagine doing a small part of the semantic rotation and then undoing it by rotation of h bar. So I see that actually this semantic rotation is equivalent to a rotation of h bar in the opposite direction. But h bar is rotated by 180 degrees to get that. So I see that it's much more convenient to discuss the analytic continuation in one variable, of course, of a function. So I would rather discuss the analytic continuation of y naught in h bar. So I slowly rotate h bar from its value to minus its value. Of course, now the Schrodinger equation, it's even easier to see that it's invariant. And under this analytic continuation, by examining the form of the, sorry, I'm missing an x here. By examining the form of the semantic notation, I see that this is exactly the solution that decays in Sk. So Sk is the kth vector. Okay, so in this way, I see that the solution that decays in this direction to infinity is related to the solutions that decay in other directions to infinity by rotations of h bar, e to the I pi k rotations of h bar. Now I will say what is very special about polynomial potentials. So for polynomial potentials, we expect that y k plus r plus 3 is equal to y minus, okay, the minus 1 comes from the normalization I chose, but minus y of k. So if I go all the way around, I get back to the same solution. If there were some singularities here for the potential in the bulk of this picture, that would make this different. I don't want to get into why it's true, but it's just that the solution to the Schrodinger equations are analytic or expected to be analytic. So there is no non-trivial monodromy by going around. And now I can, let me see. So now I'm going to start discussing the Wronskians of these different solutions and using them to define these objects that are the quantum periods. So the Wronskian, I'll write here if people need a reminder, two solutions. This depends on the UAs and the H bar, but not on the coordinate. Some conventional normalization, and I'm omitting the functional dependence. Okay, so two important properties. One, it's independent of x. And two, even more importantly, it's 0 if and only if yk is proportional to yj. Okay, now this system of all of these y's is a very redundant system storing the information about the solutions to the Schrodinger equation, because the Schrodinger equation is just a 1D ODE. So it has just a two-dimensional space of solutions. I'm not demanding normalizability for now or anything like that. So I have generally a two-dimensional space of solutions. But here I had many more. And that means that I have a lot of redundancy in the description of this, W's. And that comes into play in the Placker relations. So Placker relations can be derived by considering the change of basis between any choice of two y's, and they take this form. Maybe it's better to think about them graphically. So again, specifying to the r equals 3 case, I can take this picture and convert it to this one, where every vertex corresponds to a sector. So this vertex is 0, 1, etc. And then I can draw this relation as the sum of, for example, the sum of the products in every color is 0. Okay, so this is an important ingredient. Let me just define one more thing before I can relate everything into these quantum periods. I'll define the y variables. So let's see. I need to use a different parameterization for h bar here, but theta just encodes the h bar dependence. So y of theta is, and it will be equal, I'm telling you now, to minus log of this epsilon that that I told you before is the generalization of the quantum period. So this will be the exponents of the quantum periods. Write them down quickly. So I'm omitting the U dependence, but of course they depend on the specific potential that I choose. Okay, so again, I can represent this graphically to make it simpler to absorb. So this y2j, for example, again in the quartic case, this will be the product of the two blue Wronskians divided by the product of the two green Wronskians. And for example, so this is y2. And for example, y1 plus, I need this plus because you see here that this is shifted. So y1 plus is, I define it as y1 of theta plus I pi over 2. That will be defined as again the product of the two blue ones divided by the product of the two green ones. So now I define these objects. They are clearly something I can define, but I need to, in order to justify why I define them, I need to do two things. One is to build a system of equations that shows you that it's easy to calculate them, or that it's possible to compute them, and hence they are useful in that sense. And the second thing is to show you that they are related to, by the semi-classical limit, they are related to the classical period. So the first thing I'll do is show you that they obey an integral equation. So I'll do that using, first I will derive what's called the Y system using Placker relations that I wrote above. And then And then from there, there's a straightforward mathematical step to get the integral equation. So first, this was y plus. Now, if I want y minus, which I define as y1 minus theta minus I pi over 2, this will be drawn like this. Now the reason that this is the y, that this corresponds to y minus is because it's essentially the rotation of y plus in h bar, right? We want to, every yk that appears in the expressions for the Wronskians, we want to shift this k by, we want to shift h bar, which corresponds to shifting k. As we discussed before, again, that's too much. The analytic continuation in h bar corresponds to shifting k. So this will just correspond to shifting this picture. And now we can see that if we consider their product, so y plus of theta, y minus of theta, is actually equal to 1 plus y2 of theta. We can see this by putting these pictures one on top of the other. So we have, what is the product of these two? We have the product of these two blues and the product of these two divided by the product of 4 greens. So 1, 2, 3, 4. These two cancel among themselves. And this is exactly the picture we had before from the Placker relations. So essentially, the correct way to say it is that we have this product. We can replace it by a sum over this and this. This product and this product. When we have this product, it cancels against the greens and we get the 1. When we have this product, it is exactly this expression. So this is the y system. Essentially, this is one of the equations of the y system. Now let me straight away write the generalization. Y s plus theta y s minus theta is equal to 1 plus y plus 1 theta 1 plus y s minus 1. Okay. Okay. I hope this is more or less clear. If people have questions, I think I can spare a few minutes to. Okay.
Sorry, is it true that you don't have solutions for every polynomial? Right, because energy can take only discrete values usually.
Okay, so yes, thank you. So the solutions I'm the solutions I'm discussing now, these y's, they are not necessarily normalizable. So right now, for any energy and any polynomials that we, for any configuration that we choose, here, I lost where I was. Okay, for any configuration that we choose, for example, here we can choose any energy we want. We might not have a bound state, but that will correspond later to an extra condition of normalizability that we have to impose. So we will always have a 2-dimensional space of solutions. Does that answer the question?
Well, what I meant is that not like every energy is an eigenvalue for a particular like Hamiltonian, right? So you have a Hamiltonian solve for eigenvalues, and you have a spectrum. Then you absorb this energy like to the left-hand side, which would suggest that you shouldn't have eigenfunctions with 0 on the right-hand side. Or, yes, so you won't have solutions for every polynomial in the potential.
Right. So, so what you are saying is correct, as long as we, when we are restricting to what we usually call the Hilbert space. So when we are restricting to wave functions that decay both at plus infinity and minus infinity. So maybe I should say something about this now. So when we're restricting to solutions that decay both here and here. So but when we only ask for it to decay here, it might blow up at minus infinity, and hence usually we will not call it a part of the Hilbert space because it's not normalizable. But those type of solutions, those type of eigenfunctions exist always. They are not. They do not require the quantization of the energy. What we will impose later, we will say, okay, what is our quantization condition? The exact quantization condition in this case will be this, which is quite simple. and what it means is that the solution that decays here is proportional to the solution that decays here, and that means that it's normalizable. And when you impose also this after all of the analysis for the y functions and for when we write the TBA is valid also at the points where values of h bar and energy that you don't have bound states, that you don't have in the spectrum, but then this condition will not be satisfied. This will choose your spectrum for you. And maybe now I'm understanding that you might be asking something a bit different. So we are going the opposite way here. Instead of fixing h bar and asking what is the spectrum in the energies, we fix the energies and then we ask what spectrum of h bar do we have? What values of h bar will satisfy this? And then we can invert this relation. So generally we will have, if this is energy and this is 1 over h bar, we will have a picture like this of the spectrum. So the usual question is fixing h bar and asking what is the spectrum of energies. But in this mathematical framework, it's more convenient to fix the energy and ask what is the spectrum of h bars that is allowed.
Oh, okay.
And then we can invert this relation. So this will be after we add to the TBA will give us the exact periods, and then we will add a quantization condition that will fix these values of h bar, and then we can invert this relation.
Mm-hmm. Thank you.
Okay. Thanks. Okay, so this is the Y system. Now, as I said, the last thing I owe you is is the semi-classical limit. The limit is as h bar goes to 0 of these YAs or of these epsilon A's. So these YAs have two different types of W's. So let me go back to, for example, Y2. So as we said, the WKB approximation becomes exact as we go to the large X regime, and because these two sectors share an asymptotic region here, one can always evaluate these W's, the W's that are on the boundary of this picture. One can always evaluate them relatively easily. So even exactly. So the non-trivial parts are these two W's, and to evaluate them, what we need to do is try to understand where the WKB approximation is valid away from the large X regime. And I don't want to get into the details too much because it's just a standard WKB analysis. But there is a mathematical theorem telling us that the asymptotic expression, the WQB asymptotic expression, which I did not write down, continues to hold on paths such that the derivative of the path, gamma here is the path on the complex plane, x-plane, and such the derivative of the path is equal to plus minus this expression. And we find that these y's, again, the analysis is in the paper, but I think if I cover it here, I will lose too much time. We find that these y's have the semi-classical limit, that is the classical periods, when the turning points, so I draw as I drew before. Let me now this time draw a different potential. So if I mark these turning points, Q1, Q2, etc., to QR plus 1, then the semi-classical limit is the classical periods as long as they are ordered. So as long as the picture looks as I drew it now, and not, for example, I could have a quartic potential that looks like this, right? That has the turning points. If this is the complex X-plane, it has turning points instead of sorry, it has two real turning points, but on the complex plane also two complex turning points. So this is not here. It's this semi-classical limit will be different. So as if we start continuing these parameters a little bit away, this is of course just for real parameters. If we continue them a little bit to the complex plane, the parameters of the potential, such that these turning points move around. As turning points, I mean just zeros of the potential. If we move them a little bit, we should still have the same semi-classical limit, but at some point we will have what's called the wall crossing, which is a jump in the semi-classical limit of y. The y's, though, are completely smooth across this wall crossing. It's just the semi-classical limit that does not commute with this analytic continuation. So if anyone is interested in more details, you can ask me later. I just don't want to lose time on this. But the final result is that y is approximated as h bar goes to 0 by e to the minus ms h bar, where I chose m for the classical period just to be on par with the usual way that people, with the usual integrability literature for the TBA, but these m's are just the classical periods normalized such that m is larger than 0. But that's again just the convention. So now what we can do is we can, because we have this limit of h bar going to 0, which corresponds to theta going to infinity, we can go to the theta strip. This is very line plus I pi over 2, very line minus I pi over 2, and we can define a function that has a trivial large h bar behavior in this way. We define fs to be epsilon s minus its classical limit. So if you remember, epsilon is just the log of y. it will be more convenient to work with epsilon. So in this way, we define a function that has a trivial limit in the large theta regime. And we can now write an integral equation for it. So f of s theta So here I'm just using complex analysis to, okay, I guess I added an assumption here. So I added an assumption that there are no singularities in this regime. This I am actually not sure how to justify a priori. And actually there are cases where this is not true, but it is justified a posteriori by the fact that these equations match everything we know about the theory. I guess for the polynomial case, there should be an argument of why we do not expect the singularities on the h-bar plane. But for example, once we add angular momentum, which is one of the things, this is one of the things that actually we analyzed in our paper. If you add angular momentum and you try to analytically work with angular momentum larger than 0, which is usually the physical case, this will not be true anymore. So you will have to be careful about the singularities entering this strip. But for now, we can assume there are no singularities. We write the dispersion relation for this f of s at some point in the middle here. And then we can ask some point on the real line here. And then we can ask how can we use the y system to write an integral equation, to use this to promote this to a closed form integral equation. And of course, this can be written as the integral on the real line with fs shifted. And the important point here is that I can actually replace these f's by epsilons because there is this term will be opposite for the two. One will get I and one will get a minus I multiplying this. And now I can use the y system to replace this. Right, so the y system had y theta plus I pi over 2 y theta minus I pi over 2 on one side, and in the exponent I have exactly this sum. So I can replace it with an expression from the using the other epsilons, the expression including epsilon s plus 1 and epsilon s minus 1, and I finally get to this. I will write this in a shorthand notation, but I hope it's clear. Where this stands for convolution, k, the kernel, is 1 over 2 pi, 1 over cosh theta, and ls is log 1 plus e to the minus epsilon s, or 1 plus ys. Right? This was just ys. So this comes from applying to this the y system equation. So a crucial ingredient here was the fact that the classical limit could be subtracted, and that applies only when we have this condition, or when we are close to this condition. So as I said, this is related to wall crossing, but from the point of view, we can also derive this in this regime and then try to analytically continue to other regimes once we derive integral equation, the analytic continuation better agree with the direct derivation in the other regime. And the way we see wall crossing from the point of view of the integral equation instead of the classical limit is by seeing that as we analytically continue the parameters, these okay, I'm not giving you enough details maybe to see this right now, but the poles in these denominators will cross the integration contour when we will analytically continue in the parameter. So I want to just spend a few minutes talking about the EQC. So this was the first ingredient, which is the Y system, but that does not give us the spectrum on the nose. We need to now have some algebraic condition on the Y's such that the spectrum is quantized. So this is what's classically, or what the generalization of Bohr-Sommerfeld. So let me maybe again discuss the Quarty case just as an example. So as we discussed before, what we want is this condition, right? We want it to be normalizable. We want it to decay both in this condition, the direction and this direction. If the same solution decays in both, there is a unique solution decaying in each. The solutions must be proportional to each other, and hence this must be true. So I'm going to look for points in H bar, look for H bar, satisfying this for the energy that we already chose. And the goal, my goal would be to put this this condition in terms of purely the Y functions, so that I can use it. But that's with this drawings that we've been using, with these plots, is not so complicated, because so the condition is that this is equal to 0, and we can just shift it using an analytic continuation in H bar as we did before. So this is actually equal. So this, maybe I'll write it theta, real theta, is equal to this. And we can always, as we said before, we can always add here these. We know their values as Wronskians. So we could always multiply and divide by them. And this already looks like, so we have this at theta plus I pi. And this is already proportional to y1 of theta plus 3 I pi over 2. Because if you remember, theta 1 was the product of these two divided by this. So the condition is just this, but now we want to go back to our actual y1 variables, which means we want to get rid of this 3 I pi over 2. And the way we do this is just by using the Y system. So applying the Y system once, we have 1 over y1 theta plus I pi over 2, 1 plus y2 theta plus I pi. And then we can apply the Y system again, 1 over y1 plus, and here we have 1 plus 1 over y2. I'm omitting the dependence because it's just theta, and y plus y1 plus, y plus y3 plus. So here I just applied the y1 plus I pi over 2 times y1 theta plus I pi minus I pi over 2. So the product of these two is equal to what's inside here. And then I apply the y system again just for this y2. So this is rather technical, but it shows you that I can express this Wronskian purely in terms of the y functions that appear in my TBA. So the ones that I can solve for numerically or from another point of view, the ones that I have a good analytic handle on because I have an integral equation for them. So this is the simplest case, essentially, when R is equals 0, 2, or 3 mod 4. The derivation is pretty similar to this. If R is equal 1 mod 4, it requires a little bit more trickery, but it's nothing fancy mathematically. And of course, there is also the singular case, which I did not discuss at all. I just wrote down the Schrodinger equation in the beginning. But all of the analysis is similar, just a bit more, has a bit more details. Okay, so why is this useful to have this TBA? One could imagine if we have some Schrodinger potential, there is no problem getting the bound state spectrum from just doing a Hamiltonian notation, for example. So there are very robust numerical ways to get the spectrum. But the thing that you get here, in addition to that, is that you have a very good handle on analytic continuation. And that is the reason that we got into this originally, because we were interested in understanding analytic continuation of Ising field theory, which is a QFT. And this is a good both toy model and the limit of that theory on a small cylinder in some sense, because it would be the zero-mode quantum mechanics. So I guess what I'm trying to say is that one can hope to learn lessons about analytic continuation from this. For example, you can one simple kind of exercise that we did was try to analytically continue in the singular case where we have an angular momentum. But I'll give it as an example because I think it's nicer than the example for the polynomial potential. So we can analytically continue in the angular momentum and really probe the structure. So this is between 0 and -1 angular momentum. And what we saw is that we have this intricate. So this we saw this by using the TBA to saw this numerically by doing the TBA for very close points and reconstructing the analytic continuation from that. I am not sure how to derive this analytically, although it might be possible. And we see that, for example, this path continuation will exchange the first and second excited states. So this is very common to find in quantum mechanical models, this type of structure where as you analytically continue the spectrum in some of the parameters of the model, you can find branch points that exchange excited states or exchange resonances. I think the first branch point, if you go just around the first one, it exchanges the ground state with some very wide resonance state. I'm not sure how to interpret physically. So yeah, this is kind of the relatively simple example we wanted to try for to see that we can do it in principle. But if one is interested for some physical reason in analytic continuation, this tool will be useful for that. Okay, let me just summarize. So what you can see is that for a very big class of 1D Schrodinger problems, which is even more than I discussed today, there are also more examples. I mean, beyond the singular case that I showed today, there's a streamlined EQC plus TBA approach to use their integrability to understand the analytic structure of the spectrum. And there are some possible kind of spin-offs. So I think what Mourinho and people were trying to get at is whether afterwards this logic can be reproduced or used to learn something about the structure of resurgence in QFT. But another one that I find interesting myself is that for black holes quasi-normal modes, there are potentials with two singular points. So it's a bit more general than the than the angular momentum case, but I believe that I mean, I would say work by Al-Bagrassi and people, recent work by Al-Bagrassi and people showed that it should be possible to reproduce this story for those potentials. And from playing with it a little bit, I believe that should be possible. So I think it will be interesting for people to see it being done directly and not through the n=4 detour. Sorry, n=2 detour. Okay, I think that's all I have to say today.
Okay, thank you. Are there any questions?
Sorry, I mean, so when it comes to integrability, so what's the kind of the point that any kind of one-dimensional problem is integrable? I mean, because it seems that you have somehow integrable structure arising for any potentials. Is that the?
So if you write some, I'm sorry.
Quantum mechanically, of course. I mean, so classically it's integrable. So is the statement that it translates to quantum mechanical integrability in some sense, or? So
I mean, I guess one could hope maybe. I don't think this has been done for generic potentials in the most, but wherever you have control over the analytic structure of the wherever you have control over the analytic structure of the solutions to the Schrodinger equation, I think something like this has been done, at least something similar. Or at least I would say it can be done. There is one case which is a bit different, where you have an exponent of x in the potential, and then I think you get this y system, but it's infinite. So when you have an infinite y system, it's a bit less useful because you cannot solve it numerically. I mean, you need to truncate it. I'm not sure. I'm not an expert on this, but it seems to me a bit less control.
And maybe like a follow-up question. It's not really related to what you were saying, but say you have a system with 2 degrees of freedom. I mean, that's integrable classically. I mean, it's not at all obvious, right, that it's going to be in some way integrable even in quantum mechanics, or is it?
Very good. Thank you. Thank you for asking this. I actually forgot to say this. This is maybe the most interesting direct generalization, which is to try and do this for a 2-dimensional system or more. But yeah, let's start from 2-dimensional. I haven't managed to. We thought about it a little bit. It wasn't straightforward how to do this. I agree that the classical picture is if I have one more conserved quantity, I should be able to. It's classically integrable, and yeah, I think it's a very interesting question whether it's generalizable to those cases or to some subset of those cases.
Because there are some systems like, I don't know, say quantum Toda chain, where you have like n integrals commuting, and people say it's also quantum mechanically integrable. So
yes, yeah, I agree. But I mean about for example, the 2-dimensional, just the 2-dimensional Schrodinger equation. I'm not sure. As far as I know, this has not been done.
Yeah, it does not seem obvious, at least at all. So.
Yeah, I mean, the properties of analytic continuation should be similar, but the generalization of these Vronskians is much less useful once you start discussing a larger space of solutions.
Other questions? You mentioned relation to the Ising model. So what are these kind of coefficients of polynomials? What they correspond to?
Oh, yeah. Sorry, I don't have something too concrete to say. I'm just the Ising field theory, which is the formation of the Ising CFT with both relevant operators turned on. We would expect that if we put it on a small cylinder, we can, in the limit of a small cylinder, can think only about the zero mode quantum mechanics on that cylinder, and that I'm just saying that because of the Landau-Ginzburg description of the Ising CFT, one would expect that this would also correspond to some quartic potential. Yeah, this is a bit. I don't have a very precise statement to make about this. It's just this was one of the motivations for studying this for us specifically.
Mm-hmm. Other questions? Okay, I just was wondering about one thing. If you have only one monomial, do you have an exact solution to the problem?
Yes.
Like analytically explicit one.
Oh, sorry. Are you asking or?
Yes, if you have a just single monomial in the potential. Probably you do, right?
Perhaps. I don't know I'm sorry. I'm not sure. But I remember that there is in the ODE integrable model, the original discussions, or not original, but the discussions in the 90s about ODE-IM were for pretty simple potentials. I don't remember if it was monomials or whether they had just two coefficients that are non-zero in the polynomials. And there was already a very non-trivial PBA. So yeah, I'm sorry, I haven't thought about this.
Okay.
I guess, right, from the point of view of this, of this approach, a monomial is not so simple because a quartic monomial, for example, will be not in this regime that we discussed. Will be in this regime. Okay, right. Well, I get not monomial plus energy that shifts the, but it will be in this regime where the, if we're just talking about the monomial, the purely monomial, then it will be here, of course. That's a very singular limit of this analysis. So all four turning points collide in the middle. But yeah, so I don't know. Maybe there is another way to solve it relatively easily when it's a monomial, but I'm not aware of it.
Okay, thank you. So I don't see any other questions.
Okay, maybe I can say again that just to clarify that most of what I described today was based on work by Marinho and not on our paper. So our paper builds on it, but maybe that I feel like I need to clarify it.
Okay. Yeah. So okay, I don't see any other questions. So then thank you very much for a nice talk. Yeah, and thank you everyone for coming, and have a nice evening.
Yeah, thank you for inviting me. And thanks for the question.